Okay, now it is fine. So we understood that model predictive control, we are trying to predict our output based on the feedback from the current state of the output as well as some of the disturbance which are unmeasured, and based on that we are trying to minimize the error so that we'll get the or we'll hit the target value, or we will get the targeted output, right? And we also discuss about how to write the objective function and constraint for a MPC related problem. Now this MPC model, whatever we are discussing, commonly it is a discrete type of model, and any discrete representation of a system can be given by a state space model, right? So that also we discussed. Again, our model can be linear and can be non-linear, right? So if it is non-linear, there are multiple way to handle it, but we will mostly focus on the linear because that is the basic and everybody can understand. Non-linear, if I go, it will be a little difficult, but we can convert a non-linear problem into linear by discretizing the step size and try to fit our expected output in that range. So that can be done. So any state space model, I think Ax plus b and y of t equals to Cx plus d, where x is nothing but the state of the system and what is x dot t is nothing but the future state of the system that we are trying to predict based on the current state, that is x of t, and u is the input, y is the output, and A, B, C, D are the matrices that are connecting the input and output. So this is the state space representation. So now I will show you how you can use the MPC toolbox. We will take a very vague example of it just to understand what is the MPC toolbox is. So as I said, we can design any state space in the AX, BX form. So let us take, I'll take this matrices, two transfer function matrices, let us say G11. So you can try it at your end, but I'll just use it for reference. Okay, sorry, it is not visible. Before that, any doubt? Just a minute, it is hanging. I want to duplicate my screen. Where is that projector person? I'm not able to duplicate my screen. He's coming. A transfer function. We are considering a two input, one output system. As I said, MPC can handle n input, n output. So let us say we'll take a simple one, two input, one output system. What do you mean by input output system? Like any controller that you are designing, you will give some input, right? And based on that input, you will write the control objective to get the desired output. So this I am creating as two inputs. Is the font is very small? It's okay, fine. I'll just zoom in it. Oh, command window is getting zoomed. It's fine, right? Okay. So let us say I have a input G11 as TF, I have written TF 1 comma right. This is one of the transfer function for the, so in MPC always remember that I have to model my plant. What is my plant? The system that I want to control. Like in case of a car going on a road, if I want to control the way the car is should follow, the path the car should follow, then the plant is my car, right? In case of anything that I want to control is my plant. For the plant, if I have to do the discrete modeling using MPC, first I have to make it into the discrete format, in the state space format. So we will use the plant equation to get this state space format. So let us say for this system, the state space format is known to us, because I am giving you just an example. Later, we will try to see for a solar system that I'll discuss later. So let us say I have a input, as I said, 2 input, 1 output system. So this is one of the input G11, and this is in the form of, like it is a continuous time frame, but I'll discretize it. Okay. Then G12, let us say there is another input, because 2 input system. And let us say this input, I'll give some delay. Why it is showing error? Well, let us say we will not provide any delay, we'll keep it as simple only, like the earlier case. This is one of the system. Okay, so we have G11, let me repeat, we have G11 as this and G12 as this, right? Right. Now, because it is in a continuous time frame and I am going to design the MPC controller which will mostly work in the discrete time frame, I need to convert this into discrete. So how do we convert? In MATLAB there is a command called C2D. C2D is nothing but continuous to discrete time frame. So here this is the state space input format, so I'll write SS G11 G12 and we'll give some time delay. Positive, the second means okay. Yes, tell me. Yeah. Actually, the delay I have not considered in 2, so let us not take the delay, because if I take delay in one of the transfer function, I have to consider the delay here. Otherwise, it will be just C2D. Okay, it's too many. Okay, fine. Sampling time I have to give. right? So C to D will convert the discrete form into, continuous to discretize, and this 0.2 is the sampling time that we have given here. And now if you can see, now the conversion is to a discrete time step. So we got the A, B, C, D, because discrete time step means it will be in the form of x dot t equals to axt plus bu and y equals to this much. So we got all the A, B, C, D, that is input output related parameters, and so this is we discretized, right? Just now we have seen na, discretize means what? I have to convert into this form. So we have converted the continuous form to the discrete form using this. So we got, so if you can see, there are how many inputs? 2 inputs and 1 output system. Now we have to develop the model for this system. How to develop the model? Are you getting me whatever we are discussing? So we have given 2 input. Yeah. Fine. You take your time. I am not going to rush. How many states we are having here? How many states? 2 states. X1, X2 are the 2 states of the system. Done? Right. So for MPC, what we need? We need a model. So model is this one, right? Now using this, if I use the command m, let us say m equals to model, so we will write some m1 is equals to MPC. For writing MPC, you should have the MPC toolbox installed. If you don't have installed, this will not work. So MPC, comma, now what is the output that we have taken? G equals to, right? So G is our, and 0.2 is the delay that we have given. So this is going to create the MPC format of this. Till now, we have not yet designed the controller. I am just telling you, we don't want in ABCD format. What we want to know what is the prediction horizon, what is the control horizon, because to design the controller, we need to know, I think prediction horizon, control horizon, I don't need to again repeat, right? In the first class, we have discussed what is the prediction horizon. Exactly. So if you can see here, prediction horizon is the example that we have taken in the morning of Saturday, that 8 hours is our prediction horizon. In that, control horizon is every 1 hour that we are going to plan the activity, right? So we have a prediction horizon that need to be fixed for a particular model to be built, and control horizon, depending on my output, I can change the control horizon in between. So for MPC to get developed, I will use this MPC command, which will give you what is the control horizon, what is the prediction horizon, what is the, okay, what is weights? We have not discussed about weights, right? So what is a weight? Weight is nothing but when we are trying to reach to the, what you can say, let me, you know it, yes, Q and R matrices, but for others it may not be that obvious. So so we have written the objective function in this format, Q and R. You said that is very correct, because that is the convention we use generally. So, okay. So how is the objective function in generic form? Objective function for MPC. in generic form. So y of k plus I summation over I is equals to 1 to p minus what is our set point, right? SP, y of SP whole square we did, or I can very well write like this also, this as equals to y of k plus not y, so r of k plus I transpose q y of k plus I minus r plus summation over I equals to 1 to p del u k plus I t r del u k plus I plus summation over I equals to 1 to p okay. Well, let us say r is the set point. The set point is, let us say, it is changing with respect to the next yeah, exactly. So in this case, if you see here, this q, r and t, so these two are what? These are the constraints that we model, right? Step change in the input and the input range, right? So, and this is what? This is the main error that we are trying to minimize. I have written transpose into normal one, that is nothing but square only. Like this multiplication with this is nothing but square only, right? So this q, r and t are nothing but our weights. So q is the weight associated with the, you can say this is the weight associated with output variable, isn't it? Because we are trying to get the output y close to the set point. So this is the weight associated with the output variable, weight of output variable. What is r? Exactly. So this is the weight, or you can say the weight of manipulated variable. U is the manipulated variable in the input, isn't it? It is a manipulated variable in the input, but we are talking about the rate of change of manipulated variable del u, right? The rate of change of the manipulated variable. So we can say that this is the weight of rate of manipulated variable or manipulated variable rate. Variable rate. And what is T is nothing but weight of the manipulated variable, because it is associated with the U. If you remember the slides that we discussed in the last class, we took two things. If you see here, we said that this is also one of the constraint. The second one, yeah. So if you can see the left side of it, this one and the second one, this one and this one, right? These two are related to our manipulated variable. The del u is nothing but step change in the manipulated variable. So which is we can assign a weight to it, like the which is more closer, the step response, which one can give you more closer response towards the set point, we will give more weightage to it, and we should ensure that sum of all the weightage should be equals to 1. So that is how is the MPC. So if you see here, whenever we are writing the MATLAB one, what we are talking about now, we will get the weights with respect to weights of manipulated variable, weights with respect to manipulated variable rate, that is del u, and weight of the output variables. And it will be, if you have some manipulated variable, generally default it takes as 0. In many cases, manipulated variable, the third one we don't take, because we keep it that we know it, or we will take it as a measurement. But we need to give rates to these two for sure. Okay, because it is a default case, it has taken it by itself, that is 1 and 0.1. We have not assigned it, but it is up to the user. I can change the weights also. Okay, and if you can see here, prediction horizon, control horizon, by default it has taken as 10 and 2, but I can change also. Like as a user, we can change it. How to change it? In command window you can change it. Now can you tell me, is this model is what? Is model is kind of a structure file? Structure having combination of different variables, right? So if I say m1.model, it is nothing but, it is a structure. If you can see the field, it is a structure. It has a plant which is having 2 inputs, 1 output, disturbance, noise and some nominal values, whatever. It is a structure field. Inside the structure field, what is there? I have the plant. Inside the plant, what is there? I have the variables that we are defining, measured output, manipulated variables, everything is there. If I have to change anything, we can just simply write, let us say I want to change the prediction horizon. So I'll write simply m1.p equals to, what is the prediction horizon? It is set by default 10, right? Now let us say we want to change from 10 to 15. You simply write like this. Now you see the prediction horizon has been changed. Right? Now if you want to change the control horizon from 2 to 10, I can simply write m1.c equals to 10. Now if you see, I'll have control horizon as 10. Right? Depending on your system, you can do the hand modeling like state space of format of it. Then try to enter these values to generate the MPC model. This is how you use the toolbox of it. Now once, and let us say I have to change the plant. So what I'll do, m1.mpc, m1.model, because model is my MPC output, m1.model.plant. Okay, we have not yet designed the plant, sorry. So we have to generate the plant first. Now after this, if I have to see what are my measured variable, I'll just do m1 equals to mv. So these are my measured variable. Like in the structure, I can specify what is the minimum maximum range, what is the rate of my measured variable, that is measured variable rate, everything we can specify here. Okay. Similarly, if I have to get my what is my output variable, so I'll write OV is going, sorry, OV is going to give me the output variable. So here in output variable also I'll have, because it is a constant, so I'll have the min, minimum, maximum limit, the output variable name, the units, whatever is there. So these are the different nomenclature related to measured variable, output variable that is there inherent in the MPC. Now for this set of input, I want to design a controller. So for that, we need to open the MPC designer. In the MATLAB command window, if you write MPC designer, it is going to give you, it is going to pop up a MPC designer block. Just try it, I'll also do. For the same model, we have this model right now, isn't it? That we have given 2 inputs. What are the inputs? G11, G12, right? And we have one output, and we have given a sampling time of 0.2. For this, how is the MPC model we want to see? So MPC designer, and while writing this, you should make the D capital, otherwise you'll get error. Is opened? For me, it is taking time. Actually, in my MATLAB, some other simulings are also, still I have kept it open just to show you. For that, it is taking more time. So, not an issue. So, you will pop up a window like this. Okay. This is how, if you do MPC designer, it will pop up something like this. Here, if you go to MPC structure here, can you see this MPC structure over here? So click on that. You will get some window like this. Yeah, do it. You are not getting this window? Yeah. So is this window is open to everyone? So if you see in the top of it, we are having a generic design of the MPC structure it has shown. So MPC controller, we have a set point reference, we have some measured disturbance as input, we have some measured output as a input, then manipulated variable we have like as a input to the plant going from the MPC, and here is the output. Like this should be the structure of any MPC model that we have discussed in the previous class also. Any MPC model will have this structure. But what is the model that we are designing? It doesn't necessarily that I will have all the input. Like I may not have a unmeasured disturbance. Isn't it? The model that we are designing, let us say there is no disturbance. But for the model of the car or that vehicle road on the road, there was some unmeasured variable also. Isn't it? So it depends on the model where we are having an unmeasured variable or not. For this case, we have not at all given any, because this is a very standard system. We have only given 2 inputs, so there is no unmeasured variable. And if you see, for the variable, for the model that we have created in the command window, we have got that in G, in the name of G. Can you see here? We have model G equals to G11, G12 like that, right? So it is already, it has created that model. We are just opening that model to see how it looks like in the MPC structure. Right? And if you want to see the state space representation or the ABCD values of that, you can just click on the inspect selected system. If you do that, it will open up that ABCD value, the state space. Can you see? Yeah, you need to select the system, otherwise it will not show you. So you have to select. You can design n number of system at a time. But the system that you want to work on, just select that system and open it and see how the discrete time frame of that looks like. Then I can just create the input output of it by clicking on below. I'll see the import button. Just click on the import. If you do import, it will open up the input and output of this. But for this system, we have not given anything. So it will open, but it will not show you anything. So this is how we generally model any MPC related problem. But whatever we have written in the command window, we have to write it in the script file and run it to generate the model, state space model. Are you getting me? Here we have only written as 2 input, G11, G12. But let us say I want to design a model for the electric vehicle, or I want to design a model for particular system or plant. That plant I have to first design. For that plant I have to create the state space model of it. Then I can design the MPC controller for that. It is very slow. As you can see, it is very slow, my system. So it's taking time. It has given output as? It is step signal input. Okay. Yeah, yeah, yeah. You just see, because my system is like going a little slower, you just see what response you are getting. Yes. Here you can see here. So we are getting, based on the input, we are getting the step response output. Right? Fine. So now, up to this, if everybody follows, then let us see an example that I will run it. You don't need to do it. I'll run it, you just see. Okay? We will take a real example. So I am closing it. I'll do the clear all. Sorry. So now what we are trying to understand is, let us say we will design a MPC for photovoltaic cell. Okay. So in case of a photovoltaic cell, as we know that if the incident radiation falls on a PV system, everybody knows what is a solar PV. What does it does? It converts the radiation into heat energy into electrical energy. So if sun rays fall on it, it converts that into electrical energy. But will it convert all those incident radiation on it to electrical energy? No. So what is the efficiency of a solar cell? So we can very well relate from the efficiency. If the efficiency is close to 100%, it does convert 100% of the radiation into electrical energy. But if you see, the efficiency of a solar cell is around 11-12 is very slow. Nowadays technology has improved. Exactly. Near to 25-30. That too, if you do proper maintenance of it regularly, 30% is the efficiency. But in actual, the efficiency is around 45%. So there is a relation between temperature and efficiency in case of a solar cell. Any particular solar cell is design of some semiconductor material that can capture the heat energy and convert into electrical. That heat energy, they can sustain up to certain temperature. After that, if you overheat it, what will happen? The efficiency will reduce. Okay? And it varies from constructional wise, what is the material used, like how is the quality of the semiconductors used. It varies from also what is the area of it. Right? So now, so that means whatever radiation, if it is coming 100%, only 30 is converted into electrical, rest 70 is as a heat. If and because of the excessive heat, the efficiency is reducing, as well as your solar cell capacity is also reducing. So if we can design a controller so that we will filter out those wavelength radiation which are causing heating of the solar cell, then we can improvise the efficiency to little bit extent, isn't it? So what we are trying to do it here now, we want to design a controller which will filter out particular wavelengths which are only creating heat in the panel without doing any necessary work. Like it is not generating any output, though it is reducing the efficiency. Right? So as only a portion of the we cannot filter out radiation by some means. We can only what you can say, how we will filter out, we will tilt the panel in such a way that, yeah, exactly, some kind of control mechanism. So we are tilting, so that actually what we are trying to do, we are trying to find some relation between the outside temperature and the module temperature, and we are trying to generate a characteristics equation which will tell that for this ambient temperature, this should be the module temperature to get the maximum output. And we will try to do the tracking of the our panel such a way that those wavelength will have little effect on the panel. Okay. So this model I have taken it from a reference paper. If you can see, if total incident radiation is this much, we will have some losses through reflection radiation and some will be through, like it will give you some output, right? So this can be given by this standardized equation. What is this equation? This is nothing but rate of change of the module temperature. This is the heat or you can say the radiation absorbed by the module, and these are the losses, and this is the effective power output. So I can say total input equals to the total output, which is giving rise to temperature. Is this equation clear to everyone? I have taken a generic equation because I cannot go into pura total electrical, or I cannot go into total EC, so I have taken a in between which everyone can understand. Right? So now for this I want to design a controller. Right? So here is my photovoltaic module. I can say this is as my plant. And I want to give this plant as some lambda cutoff, like this is the cutoff wavelength. What is lambda here? Wavelength. So you cut off this wavelength, like you only accept this wavelength and cut off rest all other wavelength. So what cutoff lambda it should accept is decided by the controller. Are you getting my point? I'll give more detail. Let us say this is the figure. So here, what are the three important things that I need to design a controller, or to design a MPC based controller for any model, any plant? First is the plant, isn't it? What is the plant here for us? The photovoltaic module, solar panel. Then what input I should give it to the next is the controller, because next is the controller, right? What is the input to the controller? You tell in terms of now MPC terms you all know. What is the temperature? No, there are different temperature. Module temperature is different, ambient temperature is different. Ambient temperature is outside temperature. Exactly. We want to find out the relation between the input and the output. Output is the module temperature, input is the ambient temperature. So the set point is getting decided based on what is the ambient temperature, or you can say they are the measured variable, can I say? Isn't it? For a MPC, we will all talk about in terms of measured variable, then output variable, then disturbance, like that we will talk about. So what are the measured variable here? Ambient temperature. Wind speed also I can measure. Wind speed will also have an impact on the temperature of the panel. And also the incident radiation. How much radiation, wavelength radiation it is incidenting. So based on these three input, the reference generator is going to generate a set point. And this set point is going to be compared with the, what is the module, like the module is designed to work for a particular temperature. Above its temperature, efficiency is falling. So this is also an input to me. T module nominal is an input. That also we know. Based on this, it will calculate the delta set point, and also based on the current module temperature and nominal value of the module, it will also generate a delta module. Between these two, it will compare whichever is lesser. The controller is trying to control the temperature wavelength, right? Is this clear? So three things for any MPC controller we need. We need the plant. We need the how to generate the reference signal, and also we need to design the controller. Fine? Shall we go ahead now? What is the output of your solar panel? The power? The module power? What do you mean by power? How I will represent the mathematical equation of a power? VI, exactly. Voltage into current. But if I have n number of modules, it will be n into VI. Because n are connected in series, so I will add up them. Then the module temperature is also a output because I am measuring it. Isn't it? The input data that is given for this, let us say the module, the UV radiation falling on the module ranges from this to this, and the ambient temperature ranges from 280 to 340 because we are designing for a particular area. The module is set in, if it is in southern part of the country, the temperature will be different. If it is in the northern part of the country, ambient temperature range for a particular module will be different. If it is in some country in like some area in the Antarctica or USA, this temperature range is different because everywhere the weather is different throughout the year. So this ambient temperature range can vary based on the user. So this we have given. I have mentioned some step size just to discretize the change in the temperature in the MPC modeling. Okay. So now I will go to the this MATLAB of this like module of it, just to show you how it is designed. Yeah. So here I have the PV module code already written. So if you can see here, this is the input lambda UV, that is UV radiation. What is the range? I have already mentioned here, 300 to 430. We are varying in step size. Some IR radiation, we have infrared radiation we have taken, the value is fixed for a particular time instant. Let us say for the whole day we have taken this IR radiation, infrared radiation to be fixed. This is the ambient temperature, this is the wind speed. Okay. So these are the inputs to our model, and this is the output. So input to what? Is to the controller? No. To what? Because we are trying to calculate the PV output. We are trying to find out the relation between the T ambient and T your module. I want to show you the code of it. So here I'll show you the equation also. Here I have written the PV module code. PV cell module. This is the code. So all the input data given to the P has been to the PV module has been written here. Okay, all its heat capacity, what is. So this model has been taken from a reference paper. So if you see here the equation, this equation, this equation is nothing but has been used in the paper to in the model to implement. What is this part? What is this part? This is nothing but total. We just saw the relation now. What is this? QSW is the total radiation falling on the PV panel. So that has been mathematically modeled like this. Okay, and this alpha C, alpha I is nothing but the temperature coefficients, and FRR is nothing but the incident radiation falling on it. Lambda is nothing but the wavelength of the radiation. So we are trying to calculate the like how much is the total incident radiation. Then QTW is nothing but how much long wave radiation, in the sense getting reflected from the system. So that has been modeled like this. I am not going into the core modeling of the equation. This is nothing but the same equation here. The same equation here, we have expanded each of this term. And from where I have taken, I will also send you that paper for your reference. So if you see here, this is the paper that I have taken from. This is a paper from IEEE Journal of Photovoltaics. This I have taken. So if you see here, this is the short wave radiation. And if you see, this is the equation that we are talking about. Right? Each of these terms has been taken from this paper. Okay? This is the long wave radiation equation. This is because of the convection heat transfer, and this is the power output that we just now discussed, P equals to M into Pi. M is the number of module and Vi is the output of each module. Okay. The same has been taken here in this. Okay. So what is this? This is nothing but plant design. We want to establish the relation between the rate of change of temperature of the module because if you see here, everything is given. This range of lambda 1, lambda 2, we know. What is MA is nothing but the total area of the junction. This is nothing but A is the total area of the module. Okay. So there is junction between two modules, two cells. In a module, I can have multiple cells. Have you seen a PV system, PV module? So module is the total. In that I can have cells, and the cells are connected as a junction point. So whenever we are talking about the heat, the junction is also getting heated up, isn't it? So it has been taken, the junction has also been taken into consideration, total area has been taken into consideration, and all this refraction loss, reflection loss, everything has been taken into consideration. This is the model. Now everything here is known to us. What is the two variable that we are trying to relate? Tm and T ambient for getting maximum output. Okay. So to get maximum output, what is the relation between Tm? What is Tm? Module temperature and the ambient temperature to get maximum output. So we have designed this PV cell module. Then if we run it, now I am calling that in my function, in a function file here. If I run it, before that I need to load the data, but I think it will get loaded by itself. But let me load. So all the data I will take it from that and I'll load it, I'll run it now. Where is the editor? So if you see here, I am linearizing this model also, I will show you. It is running. It is user specific, as I told you. If you want to do it, you can do it. But whatever available is only MPPT based. Maximum power point tracking is there. It is still busy. But if you run it, I will show you the slides how when the output will get, I will show you the output. So if you run that code, I will get this as my as a output. So what is this output giving me? Now what we are doing, we are focusing on the plant now. isn't it? We are trying to find out for what value of the ambient temperature we will get the, and what should be the module temperature, so that I'll get maximum output. So if you see here, it is giving us the relation between the ambient temperature and the power output. So if you can see, if the ambient temperature is increasing, power output is decreasing. And also with the PV temperature increase, ambient temperature, like with the ambient temperature increase, PV temperature is also increasing. So if you find a linear fit of these two, the relation will come something like this between the ambient and Tm. Okay. So now the controller is trying to maintain a reference temperature by manipulating what should be the cutoff frequency that we want to filter out, so that I can generate a maximum output maintaining the temperature of the PV panel. Are you getting it? Now the model is getting linearized, because if you see here, is the model linear from this equation? Can you tell me, is the model linear? No, because it is square root, cubic root is there, right? So model is not linear. What we are trying to do is that by keeping all the values, we are trying to establish a linear relationship between the ambient temperature and the model temperature, so that we will get the maximum power output. Okay. Now if you see here, still it is running. Arey baapre. Exactly, it is continuously running actually. Somewhere it is, see, it is running in the background. Control Alt Delete I had to do. No, MPC will take a lot of your memory, that's for sure. Okay. Now after that, after the plant model is ready, what we will do next? So we are trying to, now the what you can say, we have a actual plant data, we know the actual plant data how it is. We are trying to fit the linearized model, plant model that we have built. From there we are linearizing and we are trying to find out the best fit. So if you see in this graph, I will run it in the MATLAB also, or if not, I will provide you the code also. You can see the step by step how it is. So what we are trying to do, we are linearizing the, from the relation that we got from T ambient and T model, how is the actual plant data and what is our linearized plant data. We are trying to match them, and if you see, they are closely matching. Till now we have not linearized. I have not shown you how, like what the linearization process, but I'll show you once the MATLAB is open. I have written down what are the different instructions that we need to follow to linearize the model. So just a thing is that you have to change the step size, that's all. Now let me open that. Okay, now after that, what we are trying to do, after the plant model is ready, next is what? We will represent the plant in the form of a state space representation. So if we do the state space representation of the model, we will get the system like this. Okay, this if you can very well relate, we have done it that G11, G12 kind of thing. So we have now written the plant model to get to this point. Now once this point is there, what we have to do? We have to only type in the command window MPC designer. Okay, then we will get how is the input output are getting linked. So plant model is going to give you the relations between the input and output. Then we will try to linearize the model and we will get the state space representation like this. Once this is done, we will open the MPC designer. In the MPC designer, now you will get the measured variable, you will get the output variable, everything you will get. You know what is the measured variable constraints, what is the range of it. So UV is one of our measured variable, we know the range of it. Infrared is a variable, which it's not a variable, it's a constant that we are giving to the system. Output variable, we know what is the output variable. Power is getting calculated. So power is, we are not giving. What is that? Module temperature. Module temperature. And another is ambient temperature. So these ranges are constraint. So that we have to give as a constraint in the MPC model of our MATLAB. So now I will directly run it so that it will not take much time. I feel so. Let us see. Oh. For this, I wanted it in the. Yes, it is. I am having the full place. This code is fully running. Acha. That I have to now introduce IoT in this to physically do. Yeah. Okay, this I have to make it in sync with the MPPT. Okay, so in the MPPT algorithm, I have to set this controller input, that this is the wavelength that I want to filter out. So in the MPPT algorithm, I have to give this information. Accordingly, it will try to calculate the angle and does the changes. Or we can do one thing. We are having tomorrow in the lab, right? There only. Hardware we are having in the department. So in that, the computers are faster, having more RAM size and size. So here it is taking a lot of time. It was working before. I don't know why it's very slow now. Something is taking. Okay, maybe I will close this. Everything I'll close it. Let us say he's taking. I'll close everything. Let us see. So this is the model that we will get it, as I was telling, from the temperature thing. Then now let us, I'll show you the linear model. Now plant part, I just showed you how you can generalize your plant. This is for here we are finding a relation between the ambient temperature and the module temperature. It can be anything based on what you want to design a controller for. Now let us say as an electrical engineer I can relate, I want to design a controller for, let us say, demand response. Do you know what is the demand response? So based on the changes in your what you can say load value, based on the generation, if I have to optimize my cost function as reducing electricity bill, I can design a controller to control the load inside my area or inside my house. So I can, so that is what I can say. The plant is up to you how you design it. Then after that, everything is based on your what you can say like how your variables and input and output that you are giving. Okay, I forgot to run the linearized model of it. So actually how I am doing the linearization is that I am using some of the MPC's function only. So if you see, I have reduced the step size. The step size is, if you reduce the step size, it will little slower variation giving you a linear output. So here I am using this step size 10 to linearize. Then there is something called N4 SID that because my system is now a square root of 3 like third order system. So I am using this as a thing to linearize or to find the exact fit for my input data. Then I am using some function PEM to linearize it more further. Like it depends on, in the MPC there are multiple functions, inbuilt functions are there that you can use it to linearize. So you have to see what is your nature of the non-linearity. Based on that you can find out what is the linearize of it. What is this PV model data is not found? Why it is not found? Acha, it is here na. If it is, I'll try. If it doesn't run today, then I will show it tomorrow for sure. Okay, because unnecessarily it will take time means no use. And if you see here, I am generating the state space model of this one also. If you run this, and as I say, once your model is ready, for MPC what you need for MPC what we need a model, we need model, then what we need a prediction and control horizon. Then what we need? So for any MPC model, these are the things that we need to mention. One is model. So till now whatever we have discussed in the solar is we are discuss about the model. Model is nothing but the plant of it. Then prediction control horizon, we need weights to all the variables that are involved, or outputs also. Then we need constraints. For each variable we need constraints, right? What else we need? We need a optimizer. This optimizer will MPC automatically take it as default, but you can design your own optimizer also. What else we need? So in the constraint I am considering all the variables: control variable, measured variable, output variable, disturbance, everything. What else we need? We need a state updater or state estimator. Updater or estimator. By default, if you are not writing your own state estimation updater, it will be Kalman filter. Okay, Kalman filter is the that is by default it is there in the MPC design. If you want to, as I said, some of the variables are unmeasured that you want to take into consideration to get to your set point. So for that, it by default it uses Kalman filter. Is it coming? Okay, fine. MPC optimizer. It is a MPC default. See, optimizer, as I said, if your model is linear, it is default. If it is non-linear, there are different optimizers. If it is linear, whatever we are doing will work. It will optimize. But if it is a non-linear that you cannot linearize it, there are different optimizers. Huh? In MPC. Or you can linearize your model by using some way and then use the default optimizer. What is there? So if you see here, this is the state space that I was talking about for this plant model that we have done. This is the state space equation ABCDs. Now once the state space equation are there, we can so it is taking time, right? Is it fine for you? Right now I think I can launch MPC designer. Because we have generated the state space model. Now this model will appear in the MPC designer. If you remember, for G11 and for the G model, here. Now let us click on the MPC structure. It will show us the PV module. Yes, you can see here PV linear model it is showing. So now if I click on this, I can see that state space properties that we got just now, the ABCD values, these are, right, these are there in your command window also. Now I'll import that. If I import that, it will give me the relation between the, like what are my input, how is my input, how is my output. But this output is constraint or unconstrained, whatever I will get. Constraint, but we have not yet defined the constraint within this MPC designer, right? So whatever I will get, the scale will be different. So I have to now change the input output attributes to make it within that. So if you see here, something is very like the step, because steps are not yet defined, so it is going haphazardly like somewhere else, right? So what I need to do, I'll go to the IO attribute. Okay, so from here in the IO attribute, I have to set what is IO, input output attributes. So what is the input that we are giving here is a measured variable. What is that? Wavelength, UV wavelength, right? So it is in, unit is in nanometer. The value that we can set for this one, 130. Why 130? Tell me. Can you tell me? Scale factor. Can you tell me why it is 130? Output I am just giving, that is, what is the output here? Ambient, model temperature, module temperature, Tm, that I want to plot it in, let us say, scale factor of 20, like between two values 20. And why this is 130, can you tell me? What is the UV range that we have kept initially? 300 to 430. So what is the step change that we are taking between the min and max? 130, right? So that's why this is there. Now we will do it apply. Now this is 20 I have taken. You can take it 5 also, you can take it 10 also. This is up to you. I am taking it 20. You can keep it as 10 also, no problem. So this is my output response, right? Now after that, we will go to the tuning. Why? Because now also in the output we have not considered constraint. We have only kept the range of it. Now we will go to the constraint here. Yes. So now we can fix what is our input minimum and maximum value. Tell me, what is our input minimum and maximum value? Minimum is 0. Maximum is up to how much changes I can do? 130, isn't it? In the UV variation, 0 to 130 we can vary. From 300 to 430 means I can vary at a step of any 0 to 130, right? And what is this mean? This one, output constraint, we will keep it as minus 100 to 100, let us say. This is up to you, as I said, this is up to the user. So input is a step change in the amplitude of what? What is the measured variable here? Module temperature, right? Module temperature. And what is in the output? What is in the output? Oh, sorry. Input is our UV radiation wavelength variation. Output is our module temperature. Right? So we are getting like this. Then after that, do you think that our controller has been designed? Done? Or something else is there? So see, once you design the controller, once you set all the constraint, minimum, maximum value for all the variables, and you have given a proper step size to linearize your model, everything is done. What we can do? We can use this command. What is this? Export controller. So where this controller will be taken? It will be taken to your MATLAB space here. Where is that Simulink space? Here. This is what? In the right side, this is what? This is our plant. Before the plant, I want to put the controller. So once I do the export controller, the controller will come here. Right? Then to the controller, what I have to give? What is the input to the controller? That is what? Error. Error from where? We will take input of ambient temperature, wind speed, module temperature, right? And we will use some summation or differentiation block, like difference block, to calculate what could be the wavelength that controller wants to control for, right? So I'll just quickly skip to there. So this is, I think, once is done. So you can also, what you can say, do is that you can also review your design. Whatever you have done, if you want to test it, if you want to edit that you have created, you can go to edit scenario. Okay. In the edit scenario window, it will open. Now let us say simulation time, I want to keep it to 1000. If I take 100, I may be getting larger variation, which is non-linearizing my system. We can keep it to 1000 also, 1000 or 10,000 depending on what. And we will keep it as a step response only, right? And we can change this. So this is up to us, that how we want to do it. So we can change it and linearize the model a little further. So at every time frame it will give us. Then after that we can check it whether whatever the controller we have designed, is it like giving all the attributes to the controller. So you can go to the review design. Yes, if you can see, it will give you status like this. What is this? MPC objective creation, status correct. What is Hessian matrix validation? Can you tell me? Okay. Whenever we are trying to solve an objective function, what we are trying to do? Minimize error, isn't it? If my function is linear, minimization of error means what? I am getting the slope of the curve, where the slope is 0 is my minimum point. How we are finding the slope? By taking the partial differentiation with respect to the state variable for that objective function. I think that is clear to everyone. But if my system is non-linear, then I will take double differentiation of it. What does the double differentiation will give you? Hessian matrix. Okay. So it is checking whether your system is linear or non-linear. If you see here, Hessian matrix validity, it is coming as a warning. Why? Because now I know that whatever step size I have taken for the input, I need to reduce it. Why? Because for larger, it is giving me non-linear behavior. So that's why there is a warning here. Okay. Then all other closed loop stability and everything else is clear. Your manipulated variable constraint, other hard constraint, everything is clear. Only thing is Hessian matrix validity is not there. That means it is telling you that you change the step size, reduce the step size to make it more linear. Okay. So this can be done because we know where we have kept the step size, right? We have given it in the constraint, right? Not constraint, I think. This is step size in the designer part. Here. Input output attributes. Here only we have given step size. So let us do it to scale factor to output as some 5 or 8 or something. Okay. Then we can again test. This is just I am showing different functionalities of it. Now see, the Hessian matrix has gone. We have linearized the model. So we reduce the step size to make it more linear. Now after everything is done, we can export the controller. So before exporting the controller, it is your duty to first check that whether the design is perfect or not in every sense. Whether it is linear or not and all the control parameters has been properly set or not. Okay. After that, I will do export controller. And when I do export controller, it is going to create a controller in my command window. But here it is not creating. Why? Because it is already there. I am showing you existing system. So that's why it is not. If I do yes means it will create, but it will override that one. So I don't want to disturb that one. So I'll show you that last one. With controller. So very first step of MPC controller is that I need to design the plant. Plant is this one. Okay. Do you want me to zoom it? So this one. Plant is this one. What is in the output? TMF. What is TM? Module temperature. What is P output? VI into M. Right. So this is output temperature. Lambda UV is our wavelength of the solar radiation that we have considered. This is the controller that it is getting created as a subsystem. I am opening it. Actually, this is also not controller. Till now, it is not yet done. Why? Because we have to compare. Yeah. So here if you see, this is my MPC controller. Okay. Because we don't have any major disturbance. Any MPC controller by default, if you go to your simulation new library, here if I will type model predictive control, it will show you this adaptive control, explicit MPC control, everything it will show you. Which one you should select? The normal MPC control you select. Okay, this normal one, if you take it, you can see how many input it is having. 3. What are the inputs? MO is your measured output, that you will take it as an input. What is reference? Set point. What is MD? Measure disturbance. Because in this case we don't have any measure disturbance, we can ignore it. Okay. Reference, we'll get it from the reference set point that we are creating from the linear relation between module temperature and ambient temperature. From there we'll set it, and model output is your, manipulated output is from the output. So this has been designed here. This part is our that comparison part. Okay, and then MPC is modeled as a subsystem here. Fine. And if I now run it, it is going to give you what could be the ambient temperature. It is showing some error. I know why is the error, because we have not loaded the data. At every timestamp, always remember, if I model a plant, before running the, before designing the controller, I should take all the plant data loaded in the MATLAB workspace. Then only I can design the controller. Similarly, once I take all the comparison data from your estimator, like from the whatever we are doing, what is that? Reference signal generator. Once that is created, you should first load the data to the workspace, then only you run your controller. At every, that's why I have kept in separate folder, so that you can open up one folder at a time, load the data, then you run it. So now I think it will work. No? I'll check it why it is not running. I'll give you, if you want, I'll give you this model for you to understand it further. So is this clear how we are giving? So it will come like this. Today morning only I ran and I got all the output, but why it is not running here, I am not able to find out. So this is how the MPC, as I said, it will be with the tracking system, MPPT tracking system we have to design. But as a simulation, this is how I will get the tracking results for the UV radiation range, as well as like the wavelength range that it is going to filter out. And the PV output, if you can see, the PV output is constant for throughout the day at the maximum value. This is the first hour of the simulation where it was a variation because MPC will take a little bit of time to settle down at the, because it is a controller, it has some delay also. So it will take some time to set at the point. So first hour of the simulation, you can see there is a variation in the PV output. After that, the output is constant. You run it, you will also get the same kind of output. And just let me know if you have any doubt. Right? So this I have taken it for 5 hours. The total time I have kept is 5 hours. I have divided that 5 hours into timestamps of some seconds. So I multiplied the whole second and taken it as a total time and discretize that steps into 20 steps or 30 steps depending on how at what step it is getting linearized. We have seen it is at 8 step if I take the variation, it is giving me a linearized data. Actually, we are currently started with, it is not yet ready, but it's not that confidential, it is not at all there. So, but we have started with the idea. So, we will be shortly coming up with that. Once it is done, you are very much welcome to come and see it. Right? Any doubt that I'll take? So, 3 things important in MPC controller design: plant, setting the constraints, getting a generated reference signal that you want to control, then designing the controller. That's all. And designing controller is very simple. You have to just type MPC designer. Once the design window will come, you have to just give the IO attribute, input output attributes. Check whether my model is linear, non-linear. If it is non-linear, then I have to again go and change the step size, make it linearized. What is main important is designing the plant. Okay. Thank you so much then.